Welcome back to this explainer from Forge College. In our last lesson, we covered an overview of the Solana mainnet versus devnet environment. Well, today, we're taking that knowledge and sketching out the actual architectural blueprints for moving your Solana app from a cozy testing sandbox into the harsh, unforgiving reality of production. Grab your mental hard hats and maybe a stress ball, because getting your network configuration and RPC nodes set up right, it's literally the difference between a buttery smooth launch and a total catastrophic meltdown. Okay, let's start with a pretty harsh wake-up call that so many developers face. You know the feeling. Your code is absolutely beautiful. It ran flawlessly on DevNet, but the second you deploy it to mainnet, bam, it just crashes. You're hitting rate limits, your latency is suddenly through the roof, and you are probably sweating profusely. So why does this happen? That is exactly what we're going to fix today. We'll tackle this in 5 logical phases. First, welcome to the mainnet. Second, public versus private RPCs. Third, redundancy and failovers. Fourth, data versus control planes. And lastly, telemetry and incident response. Let's dive right in. Section 1. Welcome to the mainnet, operating in a high-stakes environment. Right, so before we go off designing these complex routing strategies, we've got to understand our absolute foundational building block, the RPC endpoint. An RPC, or remote procedure call, is essentially the front door. It's the exact entry point where your application sends requests and transactions to talk to the Solana blockchain. And here's the thing. Choosing exactly where your app points those calls, that directly dictates your reliability, your speed, and ultimately your infrastructure bill. Think about it like this. DevNet is basically a super forgiving sandbox. Your RPC endpoint there, it'll silently accept incredibly heavy loads. You can spam it all day and it just nods along, maybe giving you some stale slot info, but it works. Mainnet, though, totally different beast. We're talking real economic consequences here. You are going to hit explicit rate limits and very strict compute quotas. So those lazy, long-polling strategies that worked perfectly on DevNet, oh yeah, they will actively crash your app on mainnet. Moving into Section 2, public versus private RPCs. Time to choose your foundation. Looking at the engineering spec sheet, it really comes down to a few key trade-offs. Private endpoints shield you from noisy neighbors. They give you fantastic access isolation, highly predictable throughput, and actual service level agreements. But, they cost money and take a bit more operational effort to set up. Public endpoints, on the flip side, are usually free. But the catch is, you are completely exposed to global network load. You get zero isolation and honestly very limited control over compliance. A great way to visualize this is through daily transportation. Public RPCs, they're basically shared, congested city streets during rush hour. Private RPCs are like having your own toll-paid, reserved expressway. And a self-hosted setup? Well, that's you literally mixing the concrete and paving your very own highway. How you decide to route your traffic completely depends on how fast you need to go and what you're willing to spend. All right, Section 3, redundancy and failovers. Let's talk traffic control. To build a robust system that actually stays up, you have to design redundancy to kill off single points of failure. You're usually choosing between a warm standby approach or distributing traffic concurrently. Active/passive failover routes everything to a primary endpoint, with a standby just waiting in the wings. It has low idle costs, but making that switch when things go down can be a little tricky. Active/active, however, is fully load balanced. It gives you incredibly high throughput, but, and this is a big but, it requires strict quota coordination so you don't accidentally blow past your limits across all your providers at the exact same time. Now, while our advanced courses at Forge College really get into the weeds of load balancing math, the core takeaway for you right now is just this. Divide your request volume. Splitting your traffic across multiple active endpoints ensures that if one single provider goes down, your app degrades gracefully instead of totally flatlining on your users. Which brings us to Section 4, data versus control planes, setting up our network zoning laws. Now, this mental model is absolutely crucial for your success. You really need to classify every single client action as either a state-changing control operation or just a simple data read. The control plane, that is for authoritative rights. Think transaction submissions, fee estimations, or block commitment checks. The data plane, on the other hand, is entirely read-oriented. Actions like looking up a wallet balance, pulling some token metadata, or scanning block history. If you treat these two planes exactly the same, honestly, it's a total recipe for disaster. The magic word here is separation of concerns. You want to route your critical rights to those dedicated expressways we talked about, while pushing casual reads to cached city streets. Why? Because you never want a sudden overload of read requests to crash your ability to process actual transactions. For the control plane, you might use an active/passive failover with really conservative retries, since duplicating a state change is a massive headache. But for the data plane, go ahead and use an active/active setup with caching layers pooled across public endpoints. Finally, Section 5, Telemetry and Incident Response. Time to wire up the dashboard. Picture this scenario. It's a highly anticipated NFT mint. Your users are aggressively hitting refresh on your app, your client UI is just blindly firing off retries, and suddenly you trigger massive 429 rate limit spikes from your provider, showing stale balances to your frustrated users. If you don't have a plan for this, that retry spam literally amplifies the failure and takes down your entire interface. Just a total nightmare scenario. We prevent that nightmare by having a strict automated incident response plan to back off elegantly. Step 1, your monitoring detects those 429 rate limit errors. Step 2, a client-side circuit breaker automatically kicks in to reduce the request rate. Step 3, your control plane dynamically shifts those crucial writes over to your warm standby endpoint. And Step 4, an alert triggers so your team can jump in and diagnose the root cause, all while the app actually stays alive for your users. To actually make those rapid decisions, you have to track some very specific control signals. We're talking error rates, tail latency, which, by the way, can aggressively inflate your client-side timeouts, rate limit responses, and queuing indicators. Plus, these signals act as the long-term request logs you'll absolutely need for audit-heavy applications. And remember, having a private or self-hosted path makes it so much easier to collect and retain those audit logs for any compliance investigations down the line. So, by pulling together endpoint selection, redundancy, and some smart client-side strategies, you take these theoretical concepts and turn them into a highly reliable production configuration. The big things to remember? Classify your calls by intent, data versus control. Design the redundancy pattern that actually fits that specific intent, and always map your telemetry directly to your operational decision points so your system adapts under pressure. So the big question is, how will you build your mainnet highway? Take these blueprints, prepare your checklist for our next lesson on compliance, and whatever you do, don't get stuck in traffic. Thanks for joining me on this explainer. Be sure to head over to forge.college to dive deeper into this subject and learn more about advanced Web3 infrastructure. Now get out there and build a rock-solid network.